Alrighty, so today we are going to talk about pumps again, and specifically we are going to talk about cavitation and net positive section head. Before we get into that, so cavitation. You had a homework assignment that dealt with cavitation and explained what it was. Is there someone who remembers from that homework assignment what cavitation is and would be willing to tell the class?
I could give it a shot.
Okay, Peter.
So it's when you have like a fluid flowing through a pipe and then the pressure gets really, really low and then you have little bubbles that start to form.
Yes, little bubbles start to form when the pressure gets really low. Specifically, what threshold does it have to drop below in order for bubbles to form?
The vapor pressure?
The vapor pressure, okay? If the pressure of the liquid falls below its vapor pressure, it will start to form little bubbles. And we have, for a few weeks now, been talking about how the pressure drops as you go across the pipe. So that is why this can happen. That's called cavitation. Okay. So why is that bad? Sarah, I feel like you and I talked in our office hours or about why cavitation was bad. Do you remember what we said?
Kind of like a little bit, like if they're in the swimming pool, like our homework problem, if you have like things in the swimming pool, it can like damage other equipment and things like that. Even though they're like really small bubbles.
Swimming pool, it was a swimming pool in the example in the homework, but it doesn't have to be. But the general idea is that the little bubbles collapse. So they'll just pop, and when they pop, that's a sudden change in pressure that causes a shock wave that goes through the fluid, and that's what damages equipment. As you can see in this picture, all that little pitting on the blade, that comes from cavitation. Okay, bubbles form, then they collapse. Which, give me a moment now. Yeah, I have, all right, so it forms, it collapses, and it causes a very characteristic sound, which I will have you hear as soon as I find where the controls to this meeting went. There they are. Okay. So, here we have a little video.
Electric motor with a horsepower meter through a magnetic coupling to a centrifugal pump. The pump itself is made of acrylic, so we can see the spinning impeller inside. We can also see the fluid go through. It's got a gate valve here on the discharge. It's got another valve over here on the suction. And all the piping here is clear, so we can watch the flow of fluid. Right now it's all clear water, so we can't see much in that regard. It's got a rotometer here showing us the amount of flow. But what I'm going to demonstrate here is cavitation. We're going to purposely cause cavitation to occur in the system. We're going to do so by keeping the discharge valve wide open like it is and pinching off the suction valve. What that will do is reduce the pressure in this line, and you'll see this compound gauge show a stronger and stronger vacuum as we begin to pinch off this valve. So I'll start to turn this clockwise, and you'll see the gauge's indication go down. You'll also begin to hear cavitation take effect. And we'll be able to see the bubbles form inside of here as it cavitates after it flashes into vapor and cavitates into liquid again here. So here we go, closing the valve. And watching the gauge. The gauge will go down. Minus 10 inches of mercury. Minus 12. Minus 14. You can start to hear flashing occur there. 16. More noise. Minus 18. Minus 20. You start to hear that sound that sounds almost like rocks going through the pipe. There's no debris, there's no solid material through here. That solid sounding sound is really the collapsing of the vapor bubbles as they go back into liquid form. You can really hear it now. You can see it occur inside of here. It's a very pronounced action and noise. As the water goes through the valve, it reduces pressure going to the restricted valve. Its pressure drops below the vapor point of the water at this temperature. It flashes into steam, and then after it comes out of the valve and expands again, the pressure goes up, and what happens is those vapor bubbles collapse back into liquid, and that's when we get the cavitation effect. We can see it happening here.
All right, so I wanted you to see that and to hear that sound. That sound is the distinctive sound of cavitation. If you hear it, it's generally a bad deal, okay? So a couple other things just to note from what he said. He said that when you go through a partially closed valve, the pressure drops. Does that make sense to us? All right, that's part of what minor losses are about. Specifically, he said the pressure will drop over the partially closed valve, and then it will come back up again afterwards, which is what. So it will come back up again, but it won't come back all the way to what it was before. That is what will happen over a valve like that. Okay. Okay. So that is cavitation, and we don't want it. So if you hear that sound, that is a sign that you need to do something. You also want to design your systems in the first place in order to prevent cavitation, and we're going to learn about how to do that today. So first of all, let's talk about what happens to pressure across a pump. Let's take Colin Cribbs. Hi there, Colin.
Hey.
Okay. So
How's it going?
what happens to the fluid's pressure from the inlet to the pump to the outlet to the pump? What happens to it?
The pressure increases between the inlet
Pressure
and the outlet.
increases. Yep, the pressure increases. All right. Also, do you remember from that homework you did with the cavitation, you were supposed to find the lowest point of pressure in that hose? Do you remember where that lowest point of pressure was?
I think it was right at the pump inlet.
Yeah, right at the pump inlet. Because pressure will drop all the way along the hose until you get to the pump inlet. And the pump increases the pressure across it. Inside, if we were looking to this is a centrifugal pump. So inside, what would happen is water, first say, or some liquid comes in horizontally here, and the pump creates a low pressure area sort of in the middle. And that's where there's suction. So the pump creates low pressure that sucks the water in. Then the blades spin around, add energy to the water, increase its pressure, and spit it out. The point being, so there should be the lowest pressure right there as it's getting sucked into the pump, but also the pressure might decrease at various points inside the pump. Okay, so in the pipes, the lowest pressure is going to be right there and where it goes into the pump, but then it stands to reason that the pressure will dip below that at some point inside the pump. Okay. It could even stagnate inside of there. Okay. What that means is that even if there's no cavitation in the pipe, there could be cavitation inside the pump. That's what we're establishing there. So how do we prevent cavitation? Through a concept called the net positive suction head. Zach, yes.
So I just had a question. So like if you had just, if we're not taking into account a pump, but you just have a pipe that goes like really high up, and as it goes up, the pressure is going to drop and drop. And so what happens in a pipe system if cavitation occurs, but there's no pump? Is there damage to the pipe or?
So it wouldn't go up if there was no pump. Like, water isn't going to go up a pipe unless it can. Without a
Well, like
pump,
a
it
siphon.
wouldn't
So
be
if you have
moving.
a really extreme example of a siphon, where you know the end exit.
Okay. All right, a siphon. So yes, you're right that you could get a siphon. So I suppose it seems unlikely, but maybe some kind of extreme siphon, you could drop below the vapor pressure. I'm not sure it'd be that big a problem. There wouldn't be anything it was hurting then. If it was, well, I suppose it depends on what the end of the siphon is sticking into, but I feel like there wouldn't be, if it's just a plastic tube, I feel like there wouldn't be anything it was, the cavitation collapsing would be hurting.
Okay,
That's
I was just
my
curious. I was
instinct.
just thinking. So thank
Yeah.
you.
Yeah,
Dr. Nickerson?
it's a good question, yes.
So earlier you said that when something goes through a partially closed pipe, the pressure drops, right? Which makes sense. But why does it go back up
Partially closed valve.
after?
So, okay. All right, so the pressure drops because it causes vena contracta, or the swirly feels, right? Just like with drag. So there will be, you can think of it as a low pressure wake right there. And so once it's past this low pressure wake, it will sort of speed up again and keep going. So it will recover some of the energy back, but not all of it. Some of it will just be lost to the friction and the loss of energy as it's swirling about.
Okay, cool. Thank you.
All right. So the net positive suction head is something that we define in order to help us avoid cavitation when we're designing our systems. It looks like this. So a couple things. First of all, you'll notice this is P over rho G. That puts us in head form because it's net positive suction head. Okay. Pressure over rho G. Okay, you will also notice this right here is the vapor pressure. So this is the system head at the pump inlet. So at the pump inlet, you have a certain amount of energy that's stored in the pressure of the liquid, and you have a certain amount of energy stored in the kinetic energy of the liquid. And you can express that as the head as you're going in. So what this does is it gives us the difference between the amount of head available when you enter the pump inlet and the vapor pressure. If the pressure is literally at the vapor pressure just as it's going in to the pump, it will probably drop below the pressure, that pressure somewhere inside. And so we want some amount of wiggle room. That's why this is the net positive head. And it is a suction head because there at the beginning of the pump is when the fluid is getting sucked in. I feel like I see some thoughtful eyes. Do we have any questions about that idea? Again, this is sort of just the excess amount of energy that we have going into the pump is what this represents. All right, move on.
Okay, I have a question.
Yes.
So to me, it seems like bubbles form when you have when you have a lot of energy, right? Like things boil when they have more energy. So in this case, Is it that you want more energy than the vapor pressure, or you
So
want
you
less?
want more energy, because remember, the main thing is the pressure dropping lower. So
Okay.
things boil when we have more energy. That's not really a relevant factor here. Though obviously at higher temperatures is cavitation more or less likely?
More likely.
More likely, because at higher temperatures it's more likely to vaporize. Specifically, what happens in this formula is that at higher temperatures the vapor pressure changes. Okay,
Okay.
but that's specifically what happens here. But no, in this case, having more mechanical energy as we're going in makes cavitation less likely, because the more mechanical energy we have going into the pump, the lower the pressure will dip inside of the pump, and the less likely we are to get pressure to drop below the vapor pressure. So I have two people raising your hands. Connor, first Connor, then Zach. Connor?
Is there a specific reason why this is in head form and why, say, the units aren't in pressure?
Because that's the way people do it. That's
Okay,
the only reason.
Okay, cool.
Yeah. Custom. Zach?
Oh no, mine was up from earlier. That was my bad. Sorry.
All right. Yeah, so it's just because it's custom, and people use head a lot, and we've talked a little bit about why that's a bit more convenient sometimes to just talk in terms of head, but also it's just what people do. So there are some reasons it's more convenient, but mostly it's just how it is.
Dr. Nickerson, I have a question.
Yes, Ryan.
So I read somewhere in the book where like sometimes companies will buy a stronger pump and then put like a damper on it. And is that to prevent like cavitation, or like why would you buy a pump and then like slow it down afterwards? Like buy a more efficient, or not more efficient, but stronger.
There's some reasons I can think of. I'm not sure what your book says exactly, but you might do that in order to get it to operate at a most efficient point. You might be able to save power that way by shifting when it's most efficient. You might want to have more cavitation you need, more capacity than you need, just in case. Sorry, not more cavitation, you need more capacity. Yeah. Okay, alrighty. I want to point out that this right here is the stagnation pressure that we talked about before. So we have the pressure stored in energy and this pressure stored in the kinetic energy and the velocity both together in the stagnation pressure there. Okay, so now what we're going to do, that right there, the velocity going into the pump, that's kind of an inconvenient, and the pressure going into the pump, that's a little bit inconvenient, because we would need to do some kind of mechanical energy balance to figure out what that is exactly. So instead, we are going to rearrange things to get that equation I just showed you in terms of, so you have some, let's say, one of the problems we've done before, we'd be going from point 1 to point 3, and there would just be a pump in the middle. But now we're going to go from point 1 to point 2, where point 2 is headed into the pump. And I want to put the net positive section head in terms of all this stuff at point 1 and the head loss and Z2. So I want to put that net positive section term in terms of this stuff, which we know more easily. We don't have to do some separate calculation, head loss, and the change in the height. Okay, so this is it again. So I want y'all to rearrange and find me a version of this equation, except instead of using P and V at the pump inlet, it uses these. How are y'all starting out? Like, what equation are you going to use to do this?
Mechanical energy balance.
Mechanical energy balance, yep. Okay, so I want someone to tell me what they got, but I want to wait a second because I want most people to have a chance to get all the way there. Question I have in the chat. Does this cavitation happen right before the pump, inside the pump, right after the pump, or a combination of those? So it would likely happen either before the pump, like in the homework problem. In the homework problem, we were figuring out whether it would happen before the pump or inside the pump. It is not likely to happen right after the pump because remember, right after the pump, the pressure has been raised. So the pressure is going to be higher right after the pump. Cavitation will likely happen inside or before the pump where the pressure is going to be lower.
Okay, this is another theoretical question. But
Yes,
if your pump was weak enough to where it didn't increase the pressure that much and it never went above, even at the outlet, it wasn't above the vapor pressure, would any damage actually happen to the pump?
So what you're asking is the pressure doesn't increase that much, and so maybe the well, when a shock wave collapses, that's what happens when those bubbles collapse, is it creates a shock wave, and shock waves go out in both directions. So my instinct is to say that yes, it would if cavitation happened after. So what we're saying is if it comes out of the pump, the pressure starts to drop again, and so maybe cavitation would happen again. You know what, I can't imagine cavitation happening after the pump if it doesn't happen before. I don't think you get a situation where that happens because you always have that low pressure going into the pump. If the pump can't raise the pressure enough to overcome the pressure loss that comes after it, it won't flow, it won't work. So I don't think that is a thing that would happen. If it did happen, I would think it would damage stuff. Also, it's true that maybe the bubbles would collapse less if the pressure didn't go up as much after, but I don't think that would be a situation that would occur. That is my instinct.
Okay, thanks. Just curious again.
All right. Sarah.
I just am having trouble understanding why is it not beneficial to have it in the terms of the first equation? Why do we need to change it into the two things?
Okay, well, just because most of the time, so let's say, for example, we are going from, let's say, a reservoir at atmospheric pressure up to some tank at some P2, whatever. So we're doing we are doing a problem like the kind we've done before, right? And V1 is equal to 0, V2 is equal to 0, okay? And there's just a pump in between. So if we go from point 1 to point 2, a lot of nice things happens. Like V1 and V2 are both 0, so that part of the mechanical energy balance just cancels out. We know exactly what P1 and P2 are already. Maybe P2 is at atmospheric pressure too, so that just cancels out. Just in order to figure out what the pressure and the velocity are going in there, we just have to do a whole other equation, and it's a whole other thing. Whereas generally we know what the pressure and the velocity are at our endpoints. We just don't want to have to explicitly figure out what they are going in right there. That's all. Can somebody now tell me what they got then?
Yeah, I got the new MPSH is equal to P1 over rho G plus rho V1 squared over 2 plus delta Z, or Z1 minus Z2. Oh, sorry.
Rho V1 squared over 2. Rho V squared is pressure. That's not head.
Sorry, I didn't convert it to head. V1 squared over 2G.
V1 squared over 2G, great. Plus the next part?
Delta Z, or Z1 minus Z2.
Yeah, Z1 minus Z2. I would usually delta Z means Z2 minus Z1. So it would be minus delta Z. But I'll just write it out like this. And then, what about the head loss? Where does head loss come in?
Minus head loss minus what was in the original? So vapor pressure over rho G.
Yeah, the vapor pressure, or the vapor pressure head. You're right. Good. Okay. Yep.
Can you walk through how you got that really quick?
So, Connor, would you like to say how you got that?
Yeah. So in my mind, it was the mechanical energy balance, but in reality, I just kind of realized that at P2, it will be the velocity one, pressure one, all of these minus the head loss. It'll be what it is at point 1 minus the head loss.
Yeah. So it just came from the mechanical energy balance. What I would do is, here's this. We're going in between 1 and 2, so the pump is not in between those 2 points, so that's just 0. Then I want to solve for P2 plus V2 squared. So P2 plus V2 squared over, 2G like that. And so I want P2 over rho G and V2 squared over 2G to be on the left. And then on the right, I would put everything else. So I'd move everything else over to the right. And so then I have what P2 over rho G plus V2 squared over 2G is. And then I subtract rho V, rho G. Does that make sense? Mara, was it Mara who asked that?
Yeah, it was me. I think I just need to write it down and go through it. So, but
yeah, just go ahead and write it down and do the algebra yourself, and you should be able to see. That's all. Just write out this balance. Get P2 over rho G plus 1 V2 squared over 2G on a side by itself, and you should see how it goes out. Do that yourself, and you should see it. Okay. There we go. Looks like this. Now, a few things. This should make sense to us, right? In addition to making that math work out, if we look at this, so remember, we said that the more energy you have going into the pump, the less likely cavitation is. Okay. So cavitation is less likely when net positive suction head is higher. The lower net positive suction is, the less net NPSH you have, the more likely cavitation is. So let's look at this. Head loss. The more head loss you have, will NPSH be bigger or smaller? So if you have a big head loss, will that make NPSH bigger or smaller?
Smaller.
Smaller. Does this make sense? What does head loss do to the total energy you have? Yeah, I'm seeing nods. Reagan gave a nice vigorous nod. I like that. Okay. The more head loss you have, the more energy you lose on the way to the pump, and so the more likely cavitation is. So, and then if you look at the math here, you can see that a bigger head loss means a lower NPSH. What about the vapor pressure? The higher vapor pressure is, what will happen to NPSH from this formula?
Also decrease?
It will also decrease. NPSH will decrease, right? Because the bigger vapor pressure is, and this should make sense because the higher the vapor pressure is, the smaller the difference will be between whatever pressure we have and the going into the pump and the vapor pressure. And so that is why at a higher temperature, vapor pressure goes up, NPSH goes down, cavitation is more likely. And finally, what about here? Z1 minus Z2. So what if Z1 minus Z2, if we're going down, will Z1 minus Z2 be positive or negative?
Negative?
Okay.
Positive.
Positive, right? Because like, let's say Z1 was like 10 meters and Z2 was like 5 meters or something. So if we're going down, Z1 minus Z2 is 10 minus 5 is positive 5. Okay, so a positive Z1 minus Z2, does that make cavitation more likely or less likely?
Less likely.
Less likely, right? Because if we're going down, then that actually adds energy because we're going down, so some of the potential energy that was in our fluid is going to go into the pressure and the energy going in there. What about if it was the opposite? What if we started below and we went above? So let's say we started at 5 meters and we went up to 10 meters. Then what would Z1 minus Z2 be?
Negative.
Negative. And so a negative Z1 minus Z2, going by this equation, does that make pressure more or less likely?
It makes cavitation more likely.
Rankin, was that you? Kind of quiet. But I think you said it more likely, and that's right. Okay? Because if some of the energy went into raising the fluid up, then we have less as available NPSH head going into the pump. Right. So, a couple things then. Of these two examples here, which location of the pump is better? For preventing cavitation? One on the left or A or B?
Would it be the one on the left because our delta Z would be a positive value? Not delta Z,
Yes.
Z1 minus Z2.
The one on the left is going to be better for preventing cavitation because on the left here, like this would be Z1 and this would be Z2. So Z1 minus 2 will have a bigger positive value here versus here. So that is a reason why people put pumps underneath things a lot of times, or to prevent cavitation. Another reason, so that's the big reason. Another reason is, notice that there's a shorter amount of pipe before the pump here than here. That's also significant. What does that shorter amount of pipe do for us?
Less head loss. Yeah, less head loss.
Less head loss. So there's shorter pipe, which leads to less major losses. There's also fewer fittings, though that might not be significant. But this one has one bend and a valve, and this one has two bends and a valve. Probably not a huge difference there, but it's something. So we want a shorter amount of, so first of all, we want to put the pump low, and we also want a shorter amount of pipe going into the pump than after the pump.
I have a question.
Yes.
Oh, it looks like we might actually be getting into that pretty soon. I was just going to ask how this fits in with like what we learned last Friday.
Yeah, this is exactly what we're going to talk about. Okay. So, yes.
So what happens is that NPSH value is negatives. That's when cavitation occurs, right?
Not necessarily, no.
So
it's not negative. It's just below. We're going to talk about that. That's what we're getting to next.
Okay.
Okay. All right. So I'm going to come back to you to see if the next part answers whatever your question. So looking at this is a function of flow rate, right? Because we can, the head loss is a function of flow rate. So just like on Friday, we talked about those pump curves where you do it as a function of flow rate and you can plot it. That's what we would do right here. So this is the NPSH available that you can get from the mechanical energy balance from that arrangement that we just did. This curve will be different for different liquids. Why is that? That's what I'm going to call an around person. Oh, well, okay. Hunter answered. The vapor pressure is going to be different for different liquids. Okay. Also, that means it'll be different at different temperatures. So that's the NPSH available. And then the other side of the equation is the NPSH required. So how much NPSH is needed to avoid cavitation in the pump? Connor guessed that as long as NPSH was positive, we wouldn't get any cavitation, but that's not actually quite true. So that'll mean there's no cavitation in the pipe leading up to the pump. If NPSH available is positive, then inside the pump, its pressure might drop some more. We don't know. And so we need some buffer. You need some buffer head. And how much buffer head do we need? It depends on the pump. Okay? And it also depends on the flow rate. Just in a general rule, do you think inside the pump, cavitation will be more likely at higher flow rates or lower flow rates? What do you think?
Lower flow rates?
Okay, I can see why you would think that because that's generally less energy. But actually, no. At higher flow rates, cavitation inside the pump is going to be more likely. Looks like this. So this is the NPSH required by the pump. And again, this is determined experimentally for each pump, just like the the pump curve from last time. And so just like those pump curves from last time, this is something that we get from the manufacturer. So again, here is the nice, neat version of a pump curve given, a pump chart given to you by your book. And you'll notice that it just, on a different axis, it put the required NPSH there too. So it just puts both of the things on the same chart for convenience, but it's a different axis. And here's a real world one again, to show you one that's a little bit less clear, but it still has NPSH required with a different axis here. It has both feet and meters right there. So you have the NPSH available, which is mostly, and you have the NPSH required. So the NPSH available is gonna go down as the flow rate goes up, and the NPSH required is gonna go up as the flow rate goes up, and at some point they intersect. So I'm gonna ask, actually let's ask Connor Barlow, what do you think that intersecting point represents?
Maybe the flow rate where cavitation would start to occur.
Yep, that's the flow rate where cavitation starts happening. Because that is when the NPSH we have becomes less than the NPSH we need. So that's when cavitation is going to start inside the pump.
Dr. Nicholson, I have a question.
Uh-huh.
So wasn't
Yes, Rankin.
Yeah, so wasn't the NPH equation derived based off the fact that it's going to be a positive number as long as the inlet pressure is greater than the vapor pressure? So then
Yes, it is.
And
but
then,
that
like,
doesn't mean.
Yeah.
Okay, yeah, so it will be a positive number as long as the inlet head, not just the pressure, but the inlet head is greater than the vapor pressure. And that will tell us, as long as it's a positive number, we know it can't be cavitating in the pipe going in. But that doesn't mean the pressure isn't going to drop lower at some point inside the pump.
Okay.
It's swirling around in there. It's got a suction sucking it in. There might also be stagnation points and points where there's losses and vena contracta and all that junk. So pressure is going to drop lower at some point inside that pump.
So, it's kind of like
that
a
is
pump
why
curve?
it needs to be sort of like exactly like a pump curve. Exactly like a pump curve. We know we need some extra head basically to account for stuff that happens inside the pump, and the way we find it is just through experiment.
Okay, that makes sense. Thank you.
All right.
Wait.
And looking at this one to see, like, the minimum required head is like 5 feet going into the pipe, according to this guy. 5 feet-ish, 1 meter-ish. Over here, this example. So you can see that the minimum at low flow rates is not necessarily huge. This one needs like 2 feet at this low flow rate. But yeah, you need a bit of buffer going in.
So one more time on
Ethan,
that
did you
graph.
ask something? Your box is highlighted.
Yeah. So one more time, the intersection point on that one graph, that's the V dot needed to meet the NPSH limit.
Yes. Yes, or we'll say that up until that point, so at lower flow rates going all the way up there, you're not going to have cavitation because your NPSH available is going to be more than the NPSH required. And then at that point, they cross over, And so at that flow rate and higher flow rates, you're going to risk cavitation. Because in this whole area at that higher flow rate, then the NPSH you need, which is the red line, is going to be more than the NPSH you have, which is the blue line. So what that point represents is, you could say, is the minimum, or sorry, the maximum flow rate without cavitation. So here is our problem we're going to talk about in our last minutes of class, and this is something that an engineer, and this is something I would ask a young engineer who just started to do, is something like this. So you're in your chemical plant, just started working there like 6 months ago, or maybe you're on your co-op or something. Waste is dumped into a treatment pond and then pumped to a second pond. And it's worked fine for years, and then suddenly someone reports that they are hearing sounds of cavitation. So what are some things you can check on to see what has changed? Let's try someone like Pershing, Johnny Pershing. Hey there.
Hi there, Professor.
What's something you can check to see? What's something that might be happening here, do you think?
Okay, well, if cavitation is occurring, and it's happening after a long period of time, maybe there's some buildup in our pipes that are causing some pressure loss that we didn't account for.
Yeah, some buildup in the pipe, maybe. So a clog or something causing a pressure loss, or what about corrosion of the pipe? That could do it. Someone was raising their hand. I believe it was one of the Connors, but I'm not sure which Connor.
Oh yeah, that was me. I was going to say that the epsilon must have increased because of corrosion in the pipe, which you guys just said.
Yeah. The epsilon, the roughness could increase because of corrosion or something like that. So those are things I would definitely check. Here's something. There's another answer in particular I'm kind of fishing for. Does anyone have another thought about something they could check?
Like the depth of the pond?
The depth of the pond. Who said that?
That was me.
Cameron. So the depth of that first pond, right? Because it's pond 1, pond 2. And there's a pump in between. So the depth of the first pond. Why does the depth of the first pond affect cavitation? What could have happened?
I mean, that would just change the delta Z for the whole equation that we had earlier, and
Exactly, it
small
changes
Z1 to
the
Z2
delta.
difference, it would change the NPSH. Yeah.
Right. So something that is likely that could happen is maybe the level in pond 1 has started to drop for some reason. Or maybe the level in pond 2 is going up, but the more likely version is the level in pond 1 is dropping for some reason. Maybe there's a leak, maybe something. This is something that I have heard of actually happening. It's just, or maybe there's some kind of level controller in pond 1 and it gets messed up somehow, and so it isn't maintaining the level at where it's supposed to be. So the level of the water in pond 1 drops, and so then we have a smaller height difference in between pond 1 and the pump, so we have less NPSH. Other things, I suppose it could have gotten hotter. Hopefully you should have designed your system to account for that, but I know maybe if it's a once in 100 years heat wave, then you might end up getting cavitation when you hadn't gotten it before because you just didn't design it for that that high temperature. All things to look into. All right. So, any other questions about NPSH before you all go on your merry way?
The equation we
Cameron.
found was that.
Or KK.
Sorry, that was me.
Okay,
was
cool.
the equation we found for NPSH available or NPSH required?
Available. Okay, because we found that equation from looking at the mechanical energy balance from whatever our 0.1 was to right before the pump. So the mechanical energy, what that told us is what the mechanical energy was going into the pump, and that's what's available. Because the higher the mechanical energy is going into the pump, the less likely cavitation is. That's available. Whereas required is the one that comes from just experimentally measuring on the pump.
So NPSH available is a property of the system, and then NPSH required is a property of the pump?
Yes, exactly. Just like it's analogous to the pump curve and the performance curve and the system curve from Friday. So then we had the one curve that came from the mechanical energy balance on the system and the other one that came from the pump. So in this case,
it's kind of like switched in this case, right?
Yeah, it is sort of switched because you see here that these pump performance curves go down with flow rate, and this required NPSH curve goes up with flow rate. And if I were to draw on here my curve for NPSH available, it would look something like that. And so if this is what I look like, it would mean I wouldn't want a curve that was, or I wouldn't want a flow rate that was bigger than that. So I would do that curve there, and then I would do a system curve maybe for the thing. So if this is what it would look like, then the operating point would be below the point where cavitation is happening. So this would be bad. I wouldn't want to use this pump for this system if it looked like that.
Do you think that goes back to what Ryan was saying earlier about dampening the pump? Maybe that's one of the reasons it could have done it.
Actually, yeah, cool. Maybe that would make sense if you wanted to do this and you wanted to make sure it was operating over here instead.
Okay, cool. Thank you.
So I have a question.
I had an article. Yeah, I had an article from Chemical Engineering Magazine, which was about, it was saying that a lot of people oversize their pumps because they want to be careful, and so they want to make sure their pump is big enough to get the capacity that they want, and so they oversize it, and it leads to slower efficiency. Can't remember exactly what I said, but I know. Maybe I'll read it at some point.
Okay, I have a question.
Yes.
So I'm confused why that equation we derived from the mechanical energy balance of the NPSH available, why it slopes downward with increasing volumetric flow rate. Because you have the velocity term there that make me think like it should go up.
All right, you do have that velocity term there, though generally that term's pretty small compared to the other terms. Part of this is gonna get big. One of the terms in this equation is gonna get bigger in magnitude as flow rate goes up. What is that term?
Head loss.
The head loss. So in general, the head loss is going to be a bigger factor on that than what the V1 squared is. I'm not saying there isn't a possible situation where it would be different. So there might be some possible situation out there where it wouldn't slope down like that. I don't know. I'm not sure I've ever seen it, but there could be. I don't know. But in general, head loss is going to get bigger as flow rate gets bigger, and it will make it go down. It's the same reason. It's the same reason the system curve goes up with increasing flow rate, right? Because the system curve here, this one, that tells us how much head is needed to move the fluid through the piping. And at higher flow rates, there's more head loss, and so it takes more pump head to overcome that, and so the system curve slopes up. So the NPSH available curve slopes down for the same reason the system curve down there slopes up, because of the head loss mostly.
Thank you.
Thank you.
Thank you.
Thank you. Good to see you all. It's fun times.